So this is the last installment of our electrochem videos. It's getting us to how a battery actually works. So starting off with redox, going through standard reduction potentials, here we are finally at the parts of a battery and how a battery actually generates electricity. So a couple new terms that we need to learn before we can jump into the battery idea. This organizer is page 1208. So it's actually the back side of the standard reduction potential sheet. You will notice that there is a drawing here for you to label. We're going to do a lot of labeling, so I'm thinking this drawing is a little small. You might want to redo it larger, or you're going to have a lot of lines or something. I actually have one. I'm not going to use this one. I have one that I drew that's much bigger for us to label. So it's up to you how you want to do things. All right, so the two new words that we need to learn are anode and cathode. I know you've heard those terms before. Anode is the electrode where oxidation takes place. Cathode is the electrode where reduction takes place. So anode and oxidation are the two vowels. Cathode and reduction are the two consonants. That's how I always remember which one is which. So oxidation takes place at the anode, reduction takes place at the cathode. So on a battery, when you see the plus minus charge, that's what they're referring to. All right, there are two other parts to a battery that we need to worry about. Obviously, we've got the wires connecting it to whatever the object is that's going to measure the voltage or take advantage of the voltage, the energy flow. And there's something called a salt bridge that you see here. A salt bridge is going to serve two purposes. It's going to help maintain electric neutrality throughout the whole cell in terms of charge, and it's also going to complete the circuit of negative charge. So we'll see how that works once we start looking at the structure. So if you want to pause and make the drawing a little bit bigger so you have places to label, it is entirely up to you. I am going to use this drawing as a way to help us look at things. Boy, it's really big. I didn't realize how big it was until it got covered by most of the camera. Okay, so I've already picked a couple elements. You're used to seeing silver and copper, so you're kind of used to knowing what's going to happen. So we have two beakers. And by the way, these are called Daniell cells. They're the most primitive type of battery that you can have. The parts that we're going to take a look at are true in any battery, even modern day batteries. They just don't look like this. So if you can imagine right now, I have a light bulb hooked up to it. But if you can imagine your phone or a smartwatch or something like that hooked up to two beakers containing liquid, that's not very practical. So innovations have caused batteries to get smaller and less sloppy as time has gone on. So we've got two beakers. In order to get electric current, you have to keep the two half cells separate. So one half cell will be oxidation, the other half cell, the other beaker, will be reduction. You have metal strips, which are the electrodes. The electrode is the surface where the actual half reaction is going to take place. So the exchange of electrons is going to take place right on the surface of these pieces of metal. Notice I also have solutions of the same substance because we need to have something gaining electrons and something losing electrons, and as a result, cations are involved. The wire up through whatever the object is, I'm lighting up a light bulb like I said, whatever the object is that you're giving electricity to. And then this represents our salt bridge, and again, we'll get into more details there. I've also taken the opportunity to show you that the voltages for silver and for copper, the reduction potentials, are positive 0.8 and positive 0.1, or 0.8 and 0.16. So that's where we're going to start in order to figure out what's going to be oxidation and what's going to be reduction. Notice that I haven't told you. But in order for something to act as a battery, remember that it has to have positive voltage. So in order to know which one's going to be which, we've got to look at the numbers. If I make this oxidation, this number becomes negative, which means when I add them together, overall the voltage is negative. That's not good. So this is the one that I'm going to have to make negative. So this is going to become the oxidation half reaction, or this is going to be the oxidation half cell, which means what's going on here? The reaction is going to be the loss of electrons by copper to create copper-2 ions. And what's going to happen here? Reduction, you're going to see the silver ion gain the electron to become neutral silver. So as a result of that, let's think about what's happening. Once you know what the two half reactions are, you can visualize what's going to happen inside this cell. Okay, so copper from this electrode is going to lose electrons, become copper-2 plus ions. So from the surface of that electrode, copper ions are going to be deposited into the solution. And the electrons are going to travel up the wire in that manner. So this is the oxidation half reaction, which means this is, let me write it in a different color. This is the anode, because the electrons are moving from the anode, which means this guy must be the cathode, because that's where reduction is happening. And again, this electrode is losing mass because it's losing copper atoms to the solution. So you can kind of think of the electrode as going to get worn away. Its mass is going to start to get smaller. But look what happens over here at the cathode. Silver ions come together with those lost electrons. So silver ions are going to migrate to the electrode, merge with the electrons coming from the wire, and the size of this electrode is actually going to get bigger. So just kind of a cool thing to remember. The other thing that needs to happen is the salt bridge needs to do its job. So if you think about it, in order to have electric current, I need to have a closed cycle. So electrons are flowing from right to left through the wire, which means negative charge has to flow from left to right in the solution. So that kind of says the chloride ions should be moving to the right. But let's think about why they need to do that. That's true. Chloride needs to go that way, and potassium is actually going to go the other way. But why is that? Look at what's going on here. You've got copper ions increasing the positive charge of the solution. You can't have a charged solution. That's not possible. So the chloride migrates to the anode to help maintain that neutral charge. Copper ions plus chloride ions are going to keep that solution neutral. Because remember, there's some other anion in here along with the copper ions. We just don't worry about it because it's a spectator ion. So that's why chloride is going to migrate this way. Not only does it help maintain the negative circuits, but it also maintains electric neutrality inside the anode half cell. What's going on here? We got K pluses migrating to this half cell. Why do they need to do that? Well, we're losing cations to the electrode. We're building up silver by taking the cations of silver, merging them with the electrons. So this solution would start to go negative unless the cations migrated towards the cathode. So that's kind of where these two names come from. The anode is where the anions migrate. The cathode is where the cations migrate in order to maintain electric neutrality. Because people get so confused. Why is this positive but it's called the anode? Why is this negative because it's called the cathode, and all that kind of stuff? So there's the reason, or there's one of the logical reasons. The anions migrate to the anode. The cations from the salt bridge migrate to the cathode. All right, so there's one. How about we try a second one? So I've got a new half cell here. So this one is made out of tin and iron. So I've got iron 3 plus, tin 2 plus, the iron and the tin electrodes. My salt excuse me, my salt bridge is now sodium nitrate. It's not going to make a difference. See if you can label everything like we did. What's the direction of electron flow? What's the direction of ion flow? What's the anode? What's the cathode? So on and so forth. So everything that we did the last time, pause the video, see if you can do it. So you need your old notes, obviously, to do this one. So go ahead, pause it, and give it a shot. All right, so we're back. So what do we have? We're going to start with looking at the voltages. Both of these guys are negative. So in order to maintain a positive voltage, what do I need to do? I need to flip the one that's going to guarantee a positive voltage. So this is really the one that I'm going to flip. So this is going to be my oxidation half reaction. I'm going to make it a positive voltage. So this guy is my anode. This guy is going to be my cathode. So let's write the half reactions so that we can see what's happening. Since oxidation is happening, tin is going to be losing electrons to become tin 2+. But on this side, iron ions are going to be gaining electrons to become iron neutral. Now, if we were to write the full reaction, we obviously would need to make sure that we balance the electrons. So I'm going to have coefficients in front of these guys when I put the whole cell reaction together. But for the time being, we don't really need that. So let's take a look at what's happening. Tin is losing electrons to become tin 2+. So here, what's happening? Tin ions are being added to the solution, and then the electrons are going to travel up through the wire, do whatever they do there, and finish moving down to the electrode there. So what's our half reaction? Tin loses electrons to become tin 2+. That's what's happening at the anode. At the cathode, what's happening? Iron ions are going to migrate to the electrode, and merge with the electrons that are coming through the wire to create more iron. So what's happening? We got build up here, and we've got decreasing in size there. Now, if we look at the salt bridge, the one last thing, what has to happen? Well, I'm adding tin ions here, which means the reaction is, or the half cell is getting more positive. To keep that from happening, what do I want? I want the the anions to flow this way. Here, I'm losing positive charge, so to replace it, I'm going to have the sodiums move in that direction. So the cations move towards the cathode, the anions move towards the anode, but look at my circuit. I'm completing my electric circuit of negative charge. So the electrons flow from left to right in the wire, but the anions flow from right to left in the salt bridge. So hopefully you were successful with doing that. You've got some practice problems to do to give you a little bit more